Professor, we can't hear you.
So sorry. Wait a minute. Yes. Yes. Can you hear now? That was weird. Yes. Okay. Sorry. All right. All right. I'm not going to do the whole. Okay. Thank you. Well, I don't know how that happened. Well, it doesn't matter. Thank you. I had no idea. Okay. Okay. So very quickly. Hello, Kaya. Hello, Annie. Hello, Chastity. Hello, Vanita. Hello, Brandon. Hello, Yaneli. You missed all the jokes. Good afternoon, direct chat person. Good afternoon, Kaya. Good afternoon, Chastity. Good afternoon, Brian. Good afternoon, Vanita. Good afternoon, Genesis. Good afternoon, Ariana. Good afternoon, Natalie. Good afternoon, Carlos. Good afternoon, Brian, Annie, Vanita. Thank you for telling me you couldn't hear. Good. Thank you for reaffirming Yaneli, Ariana, Chastity, Brian, Carlos, direct chat person. Okay. I don't know how that happened. Yes, I do. It doesn't matter. Okay, let's go to physics. Okay. Um, all right, so it's like back to harmonic oscillation. It's back to harmonic oscillators, right? We're shifting gears again, and this will ultimately help you with the homework four, which I believe is due next Wednesday. Now, still though, even if I'm going to say a lot today, surprise, surprise, but it's all off grid. Like everything I'm going to say today is like lecture, topic, presentation. Like imagine it's a PowerPoint, except there's no PowerPoint. Um, so like you're not going to relate this directly to homework 2 or 3, and it's not yet going to, it's all building for homework 4. More specifically, what I'm really talking about today is really going to, most of all, hopefully, help you with lab 3, which I gather you haven't started yet, I don't think. Um, so if you're looking for like application or connection, really what we're going to get into today is the stuff that will really help you with lab 3 and lab 4. Um, uh, so it's back to oscillations and ultimately waves. Uh, But as to homework for, like you need this material that I'm giving you in order to get to the point where you could do homework for. But to be totally honest, like based on everything I'm going to say today, you really could not go home tonight and do homework for. Like you still wouldn't really know what I'm at. I mean, I'm not saying yeah, you could do web research, but you still wouldn't really know what I was asking in homework for. I couldn't expect you to know what I was asking. Yeah. And you really and you could do web research, and you couldn't do it the way I want you to. So you still can't do homework 4, is what I'm saying. Now, ideally, as of Monday, you'd be able to, maybe we'll see. But to be really honest, or like to ask you for help in this, if you remind me Monday or even over the weekend, I will probably extend homework 4 further. Like I don't want you to fake it or or do it. There's wrong ways to do homework for. I don't want you to waste time on wrong ways to do it. So, or wrong ways to understand what I'm getting at. So maybe just remind me Monday, or maybe, or just someone just send me an email this weekend, then I'll probably just extend it. Okay, homework 4. But no matter what I'm trying to say right now is I just can't, I don't want you to get involved in it yet. So whatever you have to catch up on or redo for old things or whatever, do that. Um, I hope that's clear. Lastly, well, yeah, okay. So I'm gonna like start lecturing now. Um, I mean, I would ask you to take notes, of course, and write down things even that I say that I don't write, blah blah blah, the usual thing, but just don't. You know what I'm saying? All right, whatever. But also, thank you for being here today. I know it's tough to be here on a not Wednesday, so um, so thank you. Okay. All right. So I'm just going to change the view on the screen. So what I want you to picture is this. The blue is a little confusing. Hold on one second. Yeah. All right. What I want you to picture that you have a bunch. of simple harmonic oscillators or objects that are ready to become simple harmonic oscillators. You have a bunch of masses and a bunch of springs. Okay, and picture that they are identical parameters, as it says right here, i.e., identical material properties. Um, sorry, identical material properties, mass and stiffness, so that therefore they are known in advance to oscillate at identical angular frequencies and therefore identical standard frequencies and therefore identical periods, right? And just remember that is a very important and sort of fascinating feature of harmonic oscillators in general, is that any harmonic oscillator, whether it's a mass on a spring or a pendulum bob on a string or a current in an electrical circuit of a certain kind, whatever, or a weather system, remember, please, always that to be a harmonic oscillator is to be a system that cycles at a rate which is fully determined by the material properties of the system. The word for material property in physics and chemistry and science is parameter. Um, so just remember, like, if you take out a bunch of mass, so I'm asking you to picture that you're in the lab and you take out a bunch of masses like out of their boxes, and you take out a bunch of springs out of their boxes, and on the boxes say like 2 kilogram, 2 kilogram, 2 kilogram, and on the other boxes say like 200 Newton per meter, 200 Newton per meter, whatever. And the amazing thing is that you can know right. I mean, just like, it's kind of a sidebar, but it's kind of not at all a sidebar. Um, that just by taking these pieces of physical equipment out and knowing their descriptions, you already know how quickly they're going to go back and forth, regardless of how you set them up. It doesn't matter if you hold them out to here or hold them out to here. And it doesn't matter if you put them horizontally on the table or even vertically, even in gravity, as you did in lab one, right? Like, what we believe about an oscillator is that it oscillates at a certain frequency that's just fully determined by what it is, not at all how you set it up. Fascinating. So imagine that we take a bunch of these oscillators that are identical in physical property, therefore it could be expected to oscillate at identical frequencies, and that we're going to set them up so that each one of them is free to oscillate on a certain axis. Let's call it the y-axis. And then we're going to distribute them uniformly along a different axis. Let's call that the x-axis. Now, again, I mean, you could picture, like, literally in the lab, like, you could picture that x really means horizontal and y really means vertical. I mean, that makes it easy to picture. Just for the record, it doesn't need to be that way. Honestly, you could set up each one of these oscillators so that it's oscillating like this, and then they're like set up like that or something. Like, it could be both. It could be two axes of a horizontal plane. So gravity. So anything I'm about to say, I'm not relying on gravity. I'm not asking. Just like lab one, actually, if you, in a way, gravity didn't matter at all. Um, I'm not asking you to worry about gravity. I'm not saying that gravity is playing a role. I'm just saying, picture two perpendicular axes, one along which the oscillators will oscillate and the other along which they'll be distributed. Okay. And whichever one they're oscillating along, I'm going to call Y. And whichever one they're distributed along which they're distributed, I'm going to call X. Okay. So picture that. Now picture further. Did I say? Yeah. So that's like all point number one here in white. By the way, the word at the top in white, which is totally illegible, even by me, it says consider. And by that, I mean, like, this is arguably, this is like a thought experiment that could be an experiment in the lab. Like, I'm just trying to say, I'm not saying that you've done this yet, and I'm not saying it was a homework problem or anything. I'm just saying, here's something that could be done. And now we're gonna consider what the fact that it could be done has implications, physical and mathematical. So, okay, so we're considering it. So all the oscillators are identical in the way that I just described, and they're distributed in the way that I just described. And then point number two in the white, says equally spaced. Yeah. And I mean it. I mean equally spaced. I mean, in fact, so specifically, we spread these things out along an x-axis and we uniformly distribute them along that x-axis. And to be even more clear, you can sort of see by my blue lines there, we're sort of setting it up so that they're constituting or they're sitting in their own coordinate system. Okay. The x-axis, so in my mind, I'm counting oscillators. You notice here, like there's like 5 oscillators in my drawing, but the very last one is known as number 4 because the very original one in my mind is the 0th oscillator. It's like a sort of a technical point, but it's sort of important to not be confused by that. Like, in other words, I'm placing the very first oscillator on what I consider to be the y-axis, right? Or I put the edge of a meter stick right there, the edge of the meter stick, the 0th line of the meter stick, right on that original oscillator, and then assume that the next oscillator is at the 1 centimeter mark or the 1 meter mark, whatever. And then the next, so what I call that one that's at the 1 centimeter mark, call it oscillator 1. And then the next one that's at the 2 centimeter mark is oscillator 2. It's okay. Just like don't forget about 0 is what I'm saying. And I'm also saying, I'm asserting so that you can picture this, that the oscillators are in fact uniformly distributed along the x-axis. Okay. Duh. I don't mean duh, but like everything you expect is what I'm saying. Now I'm gonna get a little more fancy. Oh, sorry. Yes. Wait. Oh, yeah. Wait. I see this in the direct chat. It's like this person in the direct chat, by the way, I'm so glad you're in the class. I mean, that's true of everybody, but like, good job. Wait, because I actually have to think about what you're saying. Wait, so SH0 is aligned with the y-axis. Yes. And SH1 and SH3, I mean, oscillator 1 and oscillator 3, are aligned on the x-axis. Well, yes, according to my drawing, that is true. And I'm going to explain that part in a minute. Yeah, I mean, that is not an axis. Yes. So, yes, like the 0th oscillator definitively is on the y-axis. And then, yes, then from then on in, the heights of the oscillators, according to this picture, seem to be different heights. Like some of them happen to be right at a y=0 value. Yes, like oscillator number 1 and number 3 seem to be there, whereas oscillator 2 seem to be at like some negative y value. Yes, and yes. So let me explain that further now. What that's getting at is this. Like, okay, so there's just a summary of what we say so far. The SHOs are identical in so they're each one they're going to vibrate at the same frequency once I let them go. And each one is oscillating along the y-axis. Okay, just like it's, I'm just read this is what we already said. And the SHOs are distributed uniformly along a perpendicular axis, which we're going to call X. But then now here's the point that someone's asking in the direct chat. What I want you to notice further, and this is kind of the key to the whole thing, they're all oscillators, so they're all going to go back and forth in the y-axis, in their own little neighborhood, in their own little y-axis. Each one of them will do that. Like that's what we want. And we'll let them do that, or we will make them do that, or maybe there's even like a motor or a computer program, like whatever. But they're each going to do that. But we set them all up, like as the direct chat person is saying. Imagine that we set them all up sort of in the following way. And everything I'm about to say, I always make this sound more complicated than it is. Everything I'm about to say, if you think you get it, what I'm about to say, and you're thinking of a sort of simple interpretation of what I'm saying, then you're right. It's the simple interpretation of what I'm saying. It's not supposed to be a trick. I just sort of, but it's just really important, so I always over-explain it. So here's what I'm saying. Imagine that when you start your stopwatch, the very 0th oscillator is at the most convenient position, the amplitude position. Like imagine that the 0th oscillator, the one that's on the y-axis, is like as far from equilibrium, far above equilibrium as possible when you start your stopwatch. But at that moment, and it's like oscillating, right? And all of them are oscillating. But when you start your stop, like what you're looking at the board is like a snapshot, maybe even a snapshot of t equals 0. So when you start your stopwatch, imagine that the first oscillator, the oscillator that's at the 1 meter mark, imagine that that one is not at the amplitude position when you start your stopwatch, but is rather somewhere else. Let's say, for example, it's pi over 2 radians. Let's say it's a quarter of a cycle into its phase, into its oscillation. So whereas the 0th oscillator was at amplitude position, imagine that the first oscillator is at the equilibrium position already, like the direct chat person is asking, like I'm agreeing, right? When you start your stopwatch. And at that very moment, the next one, like the oscillator number 2 is, let's say, at the negative amplitude position. And the next one is back at the equilibrium position. And the next one is at the positive amplitude position. So in other words, imagine that the oscillators are identical in every way, except that they're staggered in phase by a constant amount. That's what I'm saying. Like exactly what you think is what I'm saying. I think if you're paying attention at all, right? Like so what I'm real so yes to the person in direct chat. Oh, awesome. Great. Thank you, direct chat person. And remember, submit for points for closing the conversational loop. And I want you all to know too. I know I get so sentimental about it, just so you know, whenever people are in the direct chat, like it is not always the same person. I just want to make clear, like, and this is a compliment to all of you. Like, talk about uniform distribution. Like, it's not. I mean, it's often a conversation at a time with one person, but there are many of you that I'm getting to know very well from direct chat. Some of you I knew last semester, some of you I didn't. I just want to make it clear that it's more than a handful of you, and I really appreciate that. And the more of you can do that, even the better. All right, so I am saying to all of you now about these oscillators. I'm saying, and I think I mentioned this last week, I'm actually asking you to picture the second simplest possible scenario of a bunch of oscillators, like the second simplest. Like the absolute simplest thing you could picture with a whole bunch of oscillators, right? That if we took a whole bunch of vertical oscillators and spread them out on a horizontal axis, the simplest thing we could do, and they were all identical, right? Which these are, the simplest thing we could do is literally set them all up, not only so that they all have identical frequencies, but that they're all in phase with each other. Like we could do that. We could set up a bunch of oscillators so that when we start our stopwatch, every single one of them is at amplitude position. That would be the simplest thing to do. But I would argue that's like a dumb thing to do. I mean, no offense. Some of my best friends do dumb things, like hang out with me. But I'm saying if you set it all up so that they all were like wah 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 to get that, you could do that. But then, like, really, why did you bother having a million different oscillators? Like, really, then whatever you're going to study or execute with that, you could have just had one long bar going up and down and up and down, right? Like, honestly. So I'm saying let's go to the next simplest thing. Let's take a bunch of vertical oscillators, vertical identical oscillators, spread them out horizontally, but stagger them in phase. Let's give them different phase constants so that we actually see something interesting. We take advantage of the fact that we have many oscillators. Let's give them all different phases, but let's stagger those phases in the simplest possible way. So whatever you're picturing in your mind is probably right, right? I'm saying like, well, one is at amplitude and the next one's at equilibrium, the next one's at negative amplitude, the next one's at, and that's just an example. It could be even more finely, like it could be that one is at amplitude and one is in between amplitude and equilibrium. And in other words, it could be pi over 4 that you're staggering them all by, or pi over 8, but some kind of constant amount, right? That's what I'm saying. Like the person in direct chat thought I was saying is what. So let's let's investigate the mathematical implications of doing that and the physical implications of doing that. Well, so let's say that we do pick the example that seems to be drawn here in the first page. Like, let's say that well, what does this say? God, my handwriting. It says, for example, let's say each simple harmonic oscillator is a quarter cycle ahead of or behind its neighbor. That's what it says, okay? I.e., Let's say each oscillator is like pi over 2 radians ahead of the next one or behind the next one. Pi over 2, right? Because 2 pi radians is a full cycle. So pi radians is a half cycle. So pi over 2 radians is a quarter of a cycle, right? Well, then we could write down an equation for each one of the oscillators. That would be a complete description for each one of these vertical oscillators and would say what it's doing along the vertical, the y-axis. Right. And we would take advantage of our new knowledge of phase constants in order to do this. So this is again, this is not the material from yesterday. This is going back to the material from Monday for what it's worth. And this is what we're going to stick on for a while. Like that other thing from yesterday, just put in your brain for the future. So the equation that would describe the very zeroth oscillator would be just what you see on the board. Y naught equals A cosine omega t plus zero, because it has zero phase because it was at the amplitude position when we started our stopwatch. Well, but the next one, the first oscillator, when we started our stopwatch, was already at the equilibrium position, a quarter of a cycle in. So the equation that describes it, everything else in the equation would be the same except for the phase constant, pi over 2, right? So we would, and stop me. I mean, I'm thinking you guys get this, but stop me if you don't, if any one of you don't. So the next one would be y1 equals a cosine omega t plus pi over 2. And then the next one would be y2 equals a cosine omega t plus 2 pi over 2, right? You see, right? And just note subtlety. So each one of these phase differs from the last one by pi over 2, but it means that at any moment, if you're measuring, if like you pick any random oscillator, the ninth oscillator, it's going to have a phase constant of 9 pi over 2, meaning that it's 9 pi over 2 radians ahead of the zeroth one, right? Like all of these are tacitly being measured relative to zero, relative to what it would look like if something were at amplitude position when we started our stopwatch. I think you get that. So it's all being measured relative to zero. So those would be all the equation. So each one would have its own equation. But you see, obviously, there is a pattern in the equations. So it should be possible for us to just collect all those equations and write one expression down that captures the entire situation. And that would look like this. So it says we could collect all these equations into one unifying expression. And that I'm looking at the chat. Okay, and that unifying expression would be down here in yellow, right? And it just says like, well, I mean, it says what it says, but what it would be useful. So, in other words, if you have this entire arrangement here, and at any given moment you want to know how high is a given oscillator at any given moment, well, you would have to specify the moment t and plug it in. But furthermore, this equation would say, well, then also specify which oscillator you're talking about, right? But the way you could specify which oscillator you're talking about is by putting in a value for x, and x isn't just a random letter. X literally means how far over we're looking on the x-axis, like what position, like x would be measured in meters, in other words. And the whole idea in advance is that we've already decided we distributed the oscillators in a certain way with regard to meters, right? So if you wanted to, so if I just walk up to you and say, hey, how high is the apparatus? How high is the mass? You would say to me, well, first of all, at what time are you looking? But second of all, where are you looking? And if I said, well, I'm looking at the ninth, I want to know after 3 seconds how high the ninth mass, the ninth oscillator is, you'd be like, oh, well, the ninth oscillator is right here at the ninth meter position, just like the seventh one is at the seventh meter position. So I'll plug in 9 meters for X. And if I plug in 9 meters for X, then that will automatically, tell this equation that I've got to be 9 pi over 2 radian, 9 halves times pi radians away from whatever the zeroth oscillator is doing. And then you plug in a value for t, like what time you're looking. And the whole equation will spit out how high that particular oscillator is at that time, right? I mean, stop me if it's not, but I mean, I think that's clear or fair. So we now have an equation that takes two independent variables. We have an equation that spits out an output based on two independent inputs. First time that's ever happened in a math class or a physics class, or I mean a science class, as far as I know, to us. But we now have like if we wanted to make well anyway, we have an equation that has two independent variables producing one dependent variable, and the equation allows us to predict how high a given mass is at a given time in this collection of masses. Okay, that's kind of interesting, kind of. But let's go a little farther. First of all, you might note pi over 2 is just an example. Like literally, this whole thing. Pi over 2 is an for me is a comfortable example to picture because pi over 2 means a quarter of a cycle. So this whole example was like what to picture, and the drawing, including the drawing that the direct chat person asked about. The drawing sort of presumed that each one of these things was staggered in phase by by a quarter cycle. That's fine, but there's no reason that they have to be. What I am demanding is that they all be staggered in phase by some constant amount. But I'm not. But I'm saying it could be any constant amount, and pi over 2 is just an easy example of a constant amount to picture. So, and again, that when I say constant amount, I mean the step in phase staggering. Like pi over 2 is the amount by which each next phase was stepped up from the last one, right? Well, it was just an example. So what if we generalized? What if we allowed pi over 2 to be like any number? Could we do that? Well, the question is any number of what's? Well, the answer I think is any number of radians per meter. Like, so this is what this is saying. I'm saying that pi over 2, it could have been pi over 4, it could have been pi over 3. I mean, it didn't even have to have the number pi in it. I mean, it's just any number as long as it's and by the way, it didn't have to be pi. It didn't anyway, sorry. But what it was, it represented how many extra radians into the cycle we're delaying per each next meter that we look along the x-axis, right? Like that number, like if you look at this equation, that number pi over 2, it's not the pi over 2 could not have just been measured in radians because x is measured in meters, right? Just like omega in this equation is not measured in radians, it's measured in radians per second. And the seconds cancel out the seconds of time so that the whole thing becomes radians. And remember, we said yesterday, 2 days, a number of days ago, we said like whatever the constant is, whatever you add to omega t, the total that you add to omega t, that has to be in radians. So in other words, pi over 2 times x, the whole package has to be in radians. And it is like for any random oscillator that you look at, say the third oscillator, the term at the end of the parentheses is 3 pi over 2. That entire thing, 3 pi over 2, is radians. And it meant 3 pi over 2 radians ahead of the 0th oscillator. So once we turn this into an equation form, we're saying it's pi over 2 times the number of meters that you look from the 0th oscillator. So the pi over 2 itself, I mean, this is a subtlety, but I want you to stay with it. The pi over 2 is not pi over 2 radians. It's pi over 2 radians per each additional meter. Multiply that by the number of meters, and you have the total numbers of pi's over 2's, right? So if you generalize that, and stop me if you oh, wait, someone just did. Oh, yes, no, totally. Someone has to leave because it's Thursday and they have to go to work. I totally get it. Yes, thank you for telling me. That was very nice of you. Watch the video. Yes, but I totally get it. It's like Thursday, not Wednesday, even though it's Wednesday, not Thursday. They used to have commercials so thank you. There used to be an ice cream company in New York called Carvel. I guess it still exists. I don't know if anybody ever goes to Carvel. There's still one. Actually, there's still one near Far Rockaway, I think. But which is relevant because we're going to talk about Far Rockaway in a second. But the point is, they used to serve Sundays at half price at Carvel on Wednesdays. This is years like when I was a kid. So they used to have this commercial that was so confusing when I was growing up, where they would say Wednesday is Sunday at Carvel, like Sunday, day of. All right, you get what I. So every time John Jay, Oh, there are. Oh, on Long Island. Oh, cool, cool, cool. Right. Okay. So, and it's great ice cream. I'm all for it. Don't get me wrong. But like, and Fudgy the Whale and all of that. But it is a thing that Fudgy the Whale is exactly the same cake as Santa Claus, just with a different. All right, whatever. Anyway, but they always used to say Wednesday is Sunday at Carvel, and I always think of that whenever John Jay declares Thursday is Wednesday. I'm always like, yes, but Wednesday is Sunday. So what the heck are we going? All right. Anyway, so stupid. Okay, inside voice. Yeah, I forgot inside voice. So I'm someone's in the chat like, can we do in the wait for the I'm looking at the chat. This is a physics thing, not a Carvel thing. For the writing in white, what does the last word say? Sorry. Yes, it says so the writing in white says, in general, the phase step could be any constant quantity of, I mean, that's what it's trying to say. Sorry. It's it's trying to say be any constant quantity of, and then under the radians per meter. And maybe tell me if you direct type person if that's what you're asking, if I cleared it up. Like so yeah, okay, great. Thank you. Thank you. That's points for thank you. No, thank you. So as usual, I'm sort of like trying to say two things at once with notation. On the one hand, I'm saying instead of pi over 2, that was just an example. From now on, let's generalize that and just call it K. K stands for any constant amount of radians per meter, right? Now, so we're going to use the symbol K to stand for that step in phase, that staggering step, the number of radians by which we increase or decrease the phase per each meter. So like that's what this little blue graph is meant to show you, but is that if you do things the way we're trying to say here, if you stagger a bunch of oscillators in the simplest possible way, what you're really saying is that if you considered a function, a graph of phase constant per, yeah, great. Okay, I was about to get to that. I was just trying to. So the answer is no. Like to Annie's question. All right, the answer is no, but a totally fair question. Hold on, it's so upsetting. I'll get to that in 1 second. But like, no, the answer is no, and it's too bad. And I wish it were a different letter, but no. So let me just finish this thing. So what I'm saying is, if you were to make a graph of phase constant per, like as a function of this position along the x-axis, you necessarily, at least the way we're setting it up, you necessarily find that it's a straight line function, a constant slope. For every meter, you increase the phase by a certain steady amount. Well, the slope of that line, the change in phi per the change in x, is what from here on in we're going to call K. We're going to call it K. And if you think about it that way, as that it's change in phi per change in position, then it has to be that K is measured, like it's a rise over a run. And it's measured in radians per meter. And to answer Andy's, yes. Okay. And I'm as upset as Andy, believe me, and I was going to say it next anyway. This K is not it's a bad coincidence. I mean, no, I really do think it's a coincidence and a bad one. This K is not the K of Hooke's law. That one's measured in newtons per meter. This one's measured in radians per meter. It's also not the K hat of K vector stuff that we were doing yet. Correct. Correct. And by the way, it's also not the K that's coming next in the curriculum known as the electrostatic Coulomb constant. It's also not that K. I know. Don't shoot the messenger. But yes, therefore, so there's like 4 Ks in this class. I, I don't know what to tell you. There are. So this one, what I try to do is I try to capitalize it and I try to put serifs on it. That's what I try to do. Like if I put serif, like those things, right? That's what you do whatever you want in your notes. But if you see a K, and I sort of try to script it also, but if you see a capital K with serifs, I mean this K. Now this K, well, wait, okay. Yeah. Now this K is very important and it's new. I'm introducing it right now, like in this class. Like, I don't believe I've ever said anything about it yet. I'm saying something about it now. It's going to play a big role in lab 3. to be really honest to all you people, because of the way the schedule worked this year, this is one of the first times in years that I'm able to give this speech before you go in for lab 3. I'm not sure quite what that's saying. I don't know if that's entirely it, but it's a good thing for you guys because lab 3 is really important. It will ultimately make a ton of sense to all of you. It like opens up the material. But when you're first doing lab 3, people are often very confused. And particularly because lab 3 starts making all these references to K that no one's ever heard of before, usually. And so the hardest part in a way of lab 3 to get your mind around is like, what is this K? And people tend to think quite reasonably that it's the K from Hooke's law, but it's not. It's this K. So in a way, what I'm giving you all here is like a big insider sneak peek trailer at what's going to happen in lab 3. Okay. And there's a name for this K. I mean, it's radians per meter right now. There's a name for it, but I'm not going to give you the name yet. I want to back up and say something like say something. Well, no, okay, I'll say it. Like what I'm saying is now if we put in that, if we focus on the top for a moment, well, focus on this. I'm saying now, if someone wanted to predict how high an oscillator was in this whole arrangement, this arrangement of phase staggered oscillators, right? This is now an arrangement of multiple oscillators. They're each oscillating on a axis, but they're all spread out or distributed along a different axis, right? and we're saying whatever, and again, I don't care how you, but whatever they're oscillating along, we're calling Y, and whatever they're distributed along, we're calling X. So if at any given moment someone wanted to know how high on the y-axis is a given oscillator, as long as you could tell them, as long as they specified two things: the point in time that they were wondering about, and the point in horizontal space that they were looking at. Like which oscillator when. As long as I told you both of those things, you would be able to predict how high the oscillator was, assuming that omega was fixed for each one of the oscillators and K was fixed, like is K pi over 2 radians per second per meter or pi over 4 radians per meter, whatever, right? So you now have a complete description. You now have an equation that has 2 inputs, 1 output for determining how high any given oscillator would be at any given time. Fascinating. But is it really fascinating? Like, okay, so why do I care so much? Why am I getting so fired up and willing to teach this on the third? Because I submit to you that if you stood back and looked at this whole arrangement, and this is where I'm going to need your help, like I'm going to need honest and not just from 3 people. Sorry, not just from 3 people. If you stood back and looked at this whole arrangement, I submit to you that you'd see something fascinating. I think like what I think you'd see if you had a bunch of oscillators going up, down, up, down, up, down, up, down, like that, right? Like they're all going up, down. Each one of them is just going up, down in its own little neighborhood, but they're all going up, down in a certain pattern, right? So each one is in a motion that is a pattern, but then there's like a pattern of the patterns, right? And I think if you stood back, well, you'd see the thing that was drawn before. Like if you stood back and watched, like at any given snapshot moment, right? At any given snapshot, you'd see this kind of shape. That may or may not be a surprise. Like, at any given moment, they're sort of all arranged in like a cosine graph, like in crests and troughs, right? But the interesting thing is that if they were all going up and down, then any given trough that you focus your eyes on would not stay at a certain spot, right? Like right now, there's a trough at oscillator number 2, and there's a crest, like sort of around oscillator 4, right? But if they were all doing this thing that I'm talking about, then a moment later, it wouldn't be the trough wouldn't be at oscillator 2 anymore. It would be more like at oscillator 3 or so, right, or at least or 2 minutes later it would be. Like the trough, you would start to see troughs and crests move horizontally, right? And in a way, like some of you might be thinking, well, yeah, duh, like duh. Okay, maybe that's a duh, but then what that means is, right, so you wouldn't just see, so at any given moment you'd see a cosine shape, and that again is partly what lab 3 is really asking you to like actually rigorously verify. But then I'm arguing more than that. You wouldn't, oh, I'm going to look at the direct chat. Oh, yeah, I see something awesome in the direct chat. And there's only one thing in the direct chat right now. So if you're the person in the direct chat, yes, that's awesome. Hold that thought for a second. But yes. Um, I'm saying not only would you see the crests and the troughs of a cosine graph, but you would see them wiggling, right? Like the whole cosine graph would be wiggling like this. And therefore, crests, and if you tracked any given trough with your eye, you would see the trough start flowing, or I mean, you would see it flowing, pulsing horizontally, and or any given crest. Like the crest would move from here to there to there to there. And then another one right behind it would be moving from here to there. There. You would see waves flowing back and forth, right? Which is basically what one person is saying in the direct chat. Like I'm arguing, you've just made a wave. And really what I'm arguing is you didn't make something that sort of like resembles kind of the impression of a wave. I think if you do this, I think what it literally makes is literally anything and everything that a wave is. Well, and I'll be rigorous about that. Well, I'll be more explicit about that in a moment. But the first thing I want to just get your verification, do you guys agree that if you did this, like if you, oh, wait, okay. So Andy's question is like the question in a way. Like, for okay, and by the way, her so hopefully you could see the chat, right? I mean, she's asking, isn't this? She's saying, well, first let me back up. Someone in direct chat said, would this be considered a wave? Would this wave be considered to have wavelength? Uh, like on oscillator 2, and I want to say yes, and I want to specifically get to yes. Like I think the distance, you could pick any two crests on this thing, and the distance between the two crests would, the length between any two crests you could call the wavelength, and that wavelength you could watch as it tracks along. Like you could pick two crests that you like and look at the gap between them, and you would see that gap move along the horizontal axis, and it would be a wavelength that you were watching move along. So I say yes to the direct chat person. Now then, Annie is saying, and I'm not blowing this off. Well, obviously I'm not blowing it off, but like, wait. Very interesting. So wait a second. So Annie's what I think Annie's acknowledging is like she knows what I'm talking about. She's saying, yeah, I could see how you could see that, but then she's saying, but isn't it like an illusion? Maybe, except then I think all waves are illusions. And I don't think they are. I mean, and I'm not like arguing with Annie. I mean, like I mean, like she's on the exactly the right mindset here. But like I want to argue ultimately that yes, this can be easy to see or hard to see depending on what you do. And yes, I like her point. Like if you like started coloring certain oscillators, it would be harder to see this wave, or more to the point, right? If you colored a certain oscillator, is that what you said? Yeah, if you made one of the spring mass systems a very different color from all the rest, a very interesting idea. For sure, that would make it easier for you to see how this is just in reality oscillators going up and down and up and down, and it'd be easier to see how how nothing, no thing is actually moving to the right or to the left. But I want to argue that if that's an illusion, that is, it's not just an optical illusion. It's it's an illusion that's fooling all of nature, not just your eyes. Let me back up for a second, and let me tell everybody again. I know sometimes I say this. I'm engaging in Annie's question right now. It is not a side question. It's not, I mean, it's great that Annie asked it. Let me make clear that you will see from the notes in a moment that it is totally is the point of the whole thing, whether she asked it or not. Okay. So I need everybody to focus on this. Don't think that this is just like a one person's, like it's not a tutoring session to any of you. Um, what I want to say, okay. In fact, let me, I'll go to the page in the notes that addresses this. I don't know why I'm so defensive. Why am I so defensive? Uh, I did say I was defensive. Why are you saying I'm defensive? I'm not defensive. Just kidding. Just kidding. Yeah. Okay. I'll go back to this page in a minute. Well, but first of all, I will say, well, let me get it straight. That K number, that K constant that's now going to go into this, the name for it is angular wave number. Because once there's a K involved, we've suddenly moved from oscillations to waves, is what I'm saying. I mean, I don't think I'm the only one saying it, but like we used to, like when you have something going up and down, that I don't care how wavy it is or how that's not a wave. When you have something going up and down, that is an oscillator. And when you draw the graph of it, the cosine graph, like y as a function of t or whatever, that's still not a wave. That is a cosine graph. It's not a wave because it's just a picture of a curve. It's a picture, a snapshot of a wiggle. It's not a wave until it's wiggling, is what I'm. And similarly, so I'm saying, first of all, I'm saying this is not a wave, and also that is not a wave. Like a drawing, just a snapshot, the blue line on page one, that's not a wave. And this is not a wave. But that is a wave, not literally, right? But if I took a bunch of these, if I took a bunch, this is oscillation in time. If I spread out a bunch of them in an intentional way through space, then I get a wave. I'm making an argument. I haven't defended myself yet. Like I'm going to explain it further. Like I haven't fully addressed Andy's illusion thing. But what I'm asserting right now is if one of these is cosines in time, if you spread it out in space and make it so that you have a cosine in space that is consisting of cosines in time, then you have a wave. Or conversely, the blue thing, that snapshot, that blue snapshot, that is not a wave. Like a snap, that moment, that blue curve, that's not a wave. But if it started going up and down in time, then it's a wave. And this is literally what you're going to do in lab 3. Lab 3, you're going to go, lab 4 is you're literally going to do what I'm doing. You're going to build up a wave from this idea. Lab 3, you're going to go reverse. You're just going to make a wave on a string. You guys are going to stand on opposite ends of a long, like thin slinky, metal slinky thing, and you're going to shake it up and down and like make curves go back and forth. You'll make waves on a slinky string. And then you're going to take videos and dissect the videos into two different graphs of y as a function of time and y as a function of space. And I'm not giving away, I mean, I am giving away the whole thing, but I'm not, but like you have to do it. I'm saying that this right here, this picture is y as a function of x. It's a cosine. If it just sits still for all of time, it ain't no wave. It's just a cosine. Similarly, if you look at one of these guys, you'll get a cosine, but that's just a cosine in time of one of these guys. Superimpose one on the other in nature or in the lab, impose cosines of time onto cosines of space, and then you have a wave. Okay, I'm getting off the, so once the K is introduced into the equation, then the whole thing becomes a wave. I still haven't proven that. I'm just arguing that. I haven't even argued it. I'm just asserting it at the moment. But that's why K is called the angular wave number. Remember, omega is angular frequency. It's angular because it's like number of radians, cycle sections per time. K is angular because it's number of radians, but it's per space. Omega is radians per second. K is radians per meter. And once you have a cosine function of both in the same phenomenon, then it's a wave. So K is called the angular wave number. Now, I'm still You can see I get very excited about this because I am asserting that we have now just finally unpacked or like presented to ourselves our first unthingy motion in the class. And this is why Annie's calling it an illusion. The reason I'm excited is because Annie has a point. There's something like, wait, is this really happening? Like, wait, what is this? And like I get what she's saying, and yes, she's absolutely right. If you colored one of the masses like a different color, it'd be or you colored a whole bunch. I mean, maybe like make this one red and this one orange and this one yellow and green, blue. Like, yes, if you focused on it in a certain way, you would see all that's happening is each individual particle is just going up and down in its own neighborhood, right? But what I'm talking about, the like illusion thing, is that if you stand back, what you see is you see something flowing horizontally, even though even though each particle is manifestly only moving vertically. If you stood back, you would sense or observe, you would have, okay, let's call it the illusion for a minute. You'd have the illusion, you'd experience the illusion of like something moving horizontally. Now, Annie's yes, very good. The connection between each point changes. I see someone totally new saying, awesome, awesome. Yes, it does. There's something key about the changes that are happening. And the connection is deep, and it is this. What Annie's calling an illusion is this sense that we would see something moving from the left to the right. She's calling it an illusion because she's correct about something very important. Something very important that she's correct about is there is no actual object moving from the left to the right. Like that's why she's saying it's an illusion. Like if you stood back, you would see a crest or if you pick a particular crest in your mind, like right, you um if you picked a particular crest in your mind, which I agree with Annie, you would not be able to paint a certain color. Like you wouldn't be able to do that. But you could fix on it with your eye. You could recognize a certain crest and you could track it as it moves from left to right. And you could track it as it moves, say, 3 meters. And you could even time it with a stopwatch and say that crest just traversed 3 meters in 1.5 seconds. You could say that crest is moving at 2 meters per second. And you could even therefore say, therefore, I predict. Like you could do physics to the crest in your mind or like on paper and say, since the crest is moving at 2 meters per second, I believe in 4 more seconds, it's going to be 8 meters over there. And you'd be correct and you'd be able to verify. Like you'd be able to track that crest number one, as opposed to crest number seven or whatever, right? You you'd be able to watch some kind of entity, crest or trough or whatever, some kind of identifiable shape. You could measure, reproduce, and predict where that shape is going to be at a certain time. And in that sense, you'd be observing and experiencing totally scientific motion along the x-axis. But Annie's point correctly is that, yeah, but there'd be no object that was moving along the x-axis, like anything you ever tried to color, which is, again, really smart. Anything that you would try to color, like with paint or something, like that's not like anything you tried to color would only be going up and down. You would never find an actual, and she's threatened, you would never find an actual object traveling along the x-axis. Yet you would be able to optically track something that's going along the x-axis, and you'd be able to do physics, analyze it with physics. And I want to go a step further and say it wouldn't even just be optical. Like you actually, like even, how can I put this? Well, here's how I could put this. Whatever it is that you'd be experiencing, whatever it is that you would do with that crest going along the x-axis that isn't actually an object, my argument is that's whatever always happens with anything that we ever call a wave. Let's say you're at Far Rockaway. Let's say you're on the beach and you're looking at the surface of the water and there's water coming in. You're like, look at the waves coming in. Look how fast they're coming in. Like, I don't want to take out my surfboard today or whatever. And you literally, like, you're seeing a water wave come in Or like, wait, child, be careful. There's a wave coming in right now. It's going to be here any moment. It's about to break. Get out, get out. Like you, right? It's like a reality. You could track these waves coming in, and then they eventually come into the sand and they break and they do damage. Or put another way, if you put a surfboard, let's be really real. You could put a surfboard on one of these wave crests in the ocean, at the beach, you put a surfboard on one, and the wave crest will carry the surfboard in or out or whatever. I.e., it doesn't even matter if you're blind. It doesn't matter if you can't like literally see it. It's not, and I'm not being picky. I mean, I am being picky, but I'm not like trying to like argue with Andy. I just want to say, wait, whatever this illusion is, it's more than optical. It's not a failure. It's not because of some funky property of our eyes. Like those crests are doing something. They could carry a surfboard, or if they were electronic, if they were currents, they could send a signal and like actually convey information as they come in, like for real. The thing that's so correct about what Annie's saying is that if you stand at the beach and you track a wave crest coming in, and you do physics on it, like, oh, it's coming in, just traveled 3 meters. It did it in 1.5 seconds. So it's going 2 meters per second. And like all of that would be correct and doable. And you can make predictions, and people do it in their heads. Surfers are obviously making predictions all the time of what the waves are going to. I'm not saying they're getting out calculators, but like we treat wave crests the same way athletes treat baseballs, right? Like they have motions that are absolutely reproducible and predictable, measurable. But the catch is that when you're watching that wave come in, consisting entirely of water molecules. Like the only thing that is at that is undergoing motions is water molecules, and yet no single water molecule needs to come in from over there to out here for there to be a wave, right? Like if you're standing at the beach watching a wave come in, a water wave come in, you're not watching what you might think you are, but if you really think about it, you're not tracking water molecules as they come in. Water molecules are just going like there's a water molecules over there going up and down and up and down, and then next to them there are water molecules going up and down and up and down, and then next to them there's water, right? I'm saying, and again, it sounds like I'm arguing. I mean, because I'm yelling, but I'm just excited because I find this so deep. I hope you could tell I'm not BSing. I find this endlessly fascinating that what you're experiencing whenever you experience a wave, in a sense, is an illusion in exactly the way that Andy said. Like all waves are an illusion in a way, in that what all waves are, it says it right here, what a wave motion is from point A to point, well, I'll just read it out loud. In English, what do we informally mean by wave motion in the first place? Answer, wave motion from place A to place B means measurable, reproducible, predictable motion. It means that measurable, reproducible, predictable motion occurred from A to B, but no individual particle traveled from A to B. That's what wave motion always means. That's why it's so interesting. Like wave motion means a bunch of stuff, different pieces of stuff just went back and forth in its own little neighborhood, and then somehow created like en masse, created a situation where then something flowed along an entirely different axis. And the thing that flowed along an entirely different axis is not a thing. That's why she's calling it an illusion. But I'm here to say it's not an illusion. I mean, if illusion means like surprising phenomenon that like isn't that is more than the sum of its constituent parts, then frick yeah, it's an illusion. But if illusion means fake, then it's not. Like it's not fake, or it's certainly not any more fake than like any other version of it. I'm going to say what I'm just looking at the. Wait, I'm just looking at the. Yeah, yeah. Well, yeah, like. Oh, in other words, one more, and tell me if you need me to go back. Another sort of informal way to put it is that wave motion is the motion, sorry, that says wave motion is the motion of a recognizable or identifiable disturbance from the equilibrium orientation of a collection of particles, collection of oscillating particles, harmonic oscillators. The oh, sorry, yes, absolutely. Sorry. I'll go back again. Yeah. And if you need me, I know my handwriting is, um, no problem. And thank you for, oh, got it. Cool. Thanks. Okay. So then this, I'm saying, what I'm really saying, and again, I'm just like, I'm saying that when you want, that if you made all these oscillators go like this, you'd eventually see something pulse across like that. The thing that you would see pulse across like that is like a crest or a trough. What is a crest or a trough? It's a recognizable shape. More to the point, it's a recognize or it's identifiable. Like trough always looks like that, and like crest always looks like that. So like you fix your eyes on some like bump, and then your eyes track the bump, and you can track the bump because it always looks like a bump. It always looks like that bump that you were originally looking at. It's like identifiable. So that bump like moves along. And it moves along, again, not in a random, like in a measurable, reproducible, predictable way. But what it is that's moving along, it consists only, let's say you do this in lab 3, where you're going to take a long piece of metal and you're going to shake the metal up and down, and you're going to send pulses going back and forth along this metal. Like you will be able to see pulses going back and forth along the metal, and they really are going back and forth. And you could even know in your heart that, like, if you shake too hard or something, one of those pulses, if it hits the other person, it's like going to hurt. Like I mean, or you could, I don't know what else or you could get it to move something. Like they're real. Um, but what is it? And each one of those pulses, and they are called a pulse, these identifiable disturbances, or a full cycle is called a pulse, like a crest plus a trough is called a pulse. But what is the pulse? Well, in the case of metal, the pulse consists of nothing but metal. But the anti-point, but the real point is that you'll see pulses going back and forth through this metal that consists of nothing but metal, but there you'll never find a piece of metal going back and forth at all. You have a bunch of little metal pieces that are each oscillating vertically in their own little neighborhood, and that creates a flow, or what we ultimately call a propagation, along an entirely different axis. The propagation is real, but it is not particular. It matters, but it isn't matter. That's what we're saying. What I'm ultimately saying is, and again, I hope it's clear. I love the fact that someone said, like, it's an illusion. Like ultimately, I am bickering with that word, I suppose, or at least I'm challenging that word, but I totally know where it's coming from. What I would say, and again, I'm only challenging it if illusion means fake. I mean, maybe this is all fake, but I don't think this example of the class, like that, is any more fake than any other. But I think the real word that we're saying, what we're saying is a wave. So like it says right here, what a wave pulse is, it's not a thing, it's a different shape of a thing, right? It's that you have this whole collection of particles that if nothing were happening at all, you'd expect them all to be along the x-axis. You'd expect them all to be in like some sort of equilibrium orientation. And then you notice disturbances, perturbations, distortions, concavities from that expected equilibrium orientation. So you start tracking with your eye or with your equipment, whatever, these disturbances that flow through the collection of particles. Well, the the disturbances are called wave pulses, and what they are, they're not objects, they are shapes or deviations from an expected shape. That's what the pulses are. And what's the collection of particles is called the medium. One thing also that you should write down that I neglected to write down is this type of motion. Then we're like, so no individual bump, no crest or trough actually, they're not things. They're happening because of things, but they are not things. So when a thing moves, we say it has a trajectory. all of physics 203, what you were looking at is trajectories of particles. And to be more clear, like any individual, any mass on any spring that's going back and forth, it's got trajectory, trajectory, trajectory. Like that's all trajectories of particles. But you put a bunch of particle trajectories together in a very specific way like this. And then next thing you know, what you have is a flow of pulses. The specific, like proper scientific term that you want to write down for flow is propagation. What these wave pulses are doing is propagating along the x-axis. Propagate just means move, but it's the word that we use when something immaterial is moving. When there is a motion of something, but the something is not a thing. Like, honestly, like I'm saying now, what we're talking about is the motion of unthingy things. That's the cute way to say it, but I mean, hopefully the relatable way to say it. But the proper way to say it is we're now talking, instead of about the trajectory of particles, we're talking about immaterial motions. We're talking about the motion of things that matter but aren't matter, i.e., we're now talking about the propagation of pulses. That's what we're talking about here. And we need particles for it to happen. Don't get me wrong. You can't, even sound waves, which we're going to get into, are pulses propagating through a medium, through a collection of particles that are oscillating, known as air molecules. And if there ain't no air molecule, I mean, even though air is a gas, it's a thing. If there's no air, then there's nothing for the sound to go, or there's no water, or no, if we're in outer space, if we're in a vacuum, then there's nothing to oscillate, then there ain't no sound. So we need particles for there to be pulses, but the collection of particles is known as a medium, and the medium just is just a sum of a bunch of little things, all individually oscillating in its own individual neighborhood along an individual axis, so that on the net result is a flow along some other axis. Again, this is like a sneak peek at what's happening in lab 3. The top graph, well, I'm like covering it up. You can't cover it. All right, that's so stupid. I'm like putting my hand on my screen, but the top graph, you're very used to at this point. Like it could have been, remember I've said a million times that the dependent variable could be X, or it could be theta, could be Y, could be Z, right? So right now we're imagining that our dependent variable is Y, like position along a vertical axis. Well, that top graph is the graph of any individual oscillator, like any fixed position along the x-axis. If we're tracking what it's doing vertically as a function of time, that's the top graph. And you already know that. That's like an oscillator, right? Where the interval between two peaks, two amplitude positions, the interval between that is a full cycle of time measured in seconds, known as the period. And so omega, angular frequency, is number of radians per that, like 2 pi radians per t, right? That we already knew that top graph. Now I'm just saying, so, and that top graph would be the graph of any one individual oscillator. That top graph is not a wave. An oscillator is not a wave. Then the bottom graph would be like if you took a snapshot, if you looked at any, so in more specific, what I'm saying. I mean, this really is like literally what's happening in lab 3. Like, and like, hopefully this is gonna make it a lot. You still have to do a bunch of stuff, but hopefully I'm making it like a lot clearer than like it usually probably is for students anyway. So the top graph, which you already know, is, if you think about it, is if you pick one position, one particular value of X, and watch as Y goes up and down as a function of time. Like you get that cosine graph on the top, right? But then if you go the other way, if you were to think about what I just did at the beginning of this class, or what you do, like if you imagine a bunch of oscillators spread out and they're all going like this, and you take a photograph at one moment, so you pick some value of t and just in other words, the first page of this entire notes, where all the oscillators are arranged at different points in their phase, but they're just like sitting there because you just took a snapshot, right? Then y is a cosine function of x, right? So now this second graph is y as a function of x. To be clear again, we've never looked at that before. We were always just looking in one, we were always just assuming x was, you know what I'm saying? We never looked at that before. But now I'm saying, look at that. Look at a snapshot of the blue of all the oscillators arranged at different points in their phase, and that's a cosine graph as well. Well, the interval between any successive crests on that graph, or two successive peaks on that graph, that's the distance measured in meters between any two crests, right? You know, from seventh grade or whatever else, that length measured in meters is called the wavelength, or in other words, lambda, right? So lambda is like to space as capital T is to time. And similarly then, K is how many cycles we're getting, how many cycles, how many radians are being traversed or executed per that amount of space. So I'm ultimately saying K is to space as omega is to time. And you need to have both happening in order to make a wave. If you have cosinusoidal oscillation of time and space together in one phenomenon, then you have a wave. And what that means in English is then you have some kind of immaterial disturbance propagating through a material medium, right? If you put omegas to, if you can describe your phenomenon with this equation at the top of the board, if you have a situation where for at any given moment and any given point on a given axis, you find a new point in a different axis, and right, if you have cosines occurring in time and space imposed together, that's a wave. We have 2 minutes. I'm going to say it one more time. This is not a wave. And this is not a wave. A cosine in time, the top graph, is not a wave. A cosine in space, the bottom graph, is not a wave. But a bunch of time cosines spread out in space is a wave if they're spread out properly, arranged properly, phase staggered like this. And a space cosine wiggling in time is a wave. And either one, you stand back and look, and you'll see crests and troughs going back and forth along an axis. You'll see motion that you can measure, or you don't have to see, you could be blind, but you'll experience motion that you can measure, reproduce, and predict. But for which you could associate or identify no single material particle in the world. Bottom line, when water waves move toward your face, something moves toward your face, but it ain't no, and it's only there because of water, but there ain't no thing of water coming toward your face. That's what I'm saying. I'm going to leave. I mean, have a great, I'll see you Monday. Don't try to do any new homework. Just do the homework you're already on. I'm going to stop the recording. I hope that made any sense.